Okay, I like the thing in Gertrude's talk about um, the problem. Samarium hexaboride is not a cabbage, like most F-electron systems. The data is changing extremely rapidly, so the number of I want to present something which is actually a little bit of theory and also a little bit of an experiment. The experiment was done by Alex Gray and his students and a team of people in Germany who don't appear on the slide, and also Thomas Durakiewicz. The samples came from Zach Fisk and Priscilla Rosa. Okay. So I'm going to skip the outline and give you a little bit of background to what I'm going to talk about, which is starting out with the bulk. We think that the bulk is just a hybridization gap material, so you have this flat F level and hybridizing with a sort of conduction band, which is this parabolic-like thing. And the thing to note is that there are two gaps. A direct gap that which is a Q equals 0 transition from the red to the blue bands, vertical transition, which has a magnitude of twice the hybridization gap, hybridization matrix element, which should be renormalized. And then there's an indirect gap which goes from the zone boundary to the zone center. These were shown beautifully in the data by Piri yesterday. And if you're looking at the indirect gap, that shows up quite strongly if you look at the total density of states. So you find the thing on the right panel, and you can then describe this thing as a semiconductor or an insulator just by putting the Fermi energy in the gap. One of the things about the gap in samarium hexaboride is that it has a magnitude of order of 20 millielectron volts, which is very narrow. This just suggests that there's some very large many-body effects due to the Coulomb interactions between the electrons in the F shell. This is samarium hexaboride, if you think about it as a condo insulator, then falls into the same class as a number of other materials like cerium-3, bismuth, 4, platinum-3, which has a larger gap than was first studied by Mike Hundley, and also the neutron scattering work by Andrea Severing was here. But one of the things about this low temperature gap is that, or indirect gap, is you can see it in a number of thermodynamic measurements, and it's extremely temperature dependent, and it's as shown here. So why is this gap small? Well, you can really understand this by using the Slave boson method invented by Piers Coleman, where you project out states with double occupancy by introducing Lagrange undetermined multipliers such that the number of F quasi-particles plus the number of bosons is equal to 1. And that sort of projects out, as I said, double occupancy in cerium. And what that means is that you have to replace the F operators, the F electron operators, by product of F quasi-particle operators and the boson operator. And that has the effect of turning the mixing or the hybridization between the F and conduction band to something which involves 3 particle operators. That is, it includes the boson field in there. So one thing one can immediately do is to say that the boson field can condense at low temperature, and that essentially gives you a renormalization of the hybridization matrix by a factor of 1 minus NF, because of the constraint that the number of bosons is equal to 1 minus NF, and the F level gets shifted up to the Fermi level. That has 2 effects. One, the shifting up The shifting up of the F level just means that you have less F electrons, and so you're reducing the Coulomb interaction between them. And the other thing, which you probably already know, is that the reduction of the hybridization matrix elements just represents the blocking effect of having an F electron in a particular level. The conduction electron cannot hop into that state, and so on average the hybridization matrix element is reduced. So that gives you a temperature-dependent reduction in the hybridization matrix element. In the mean field theory, that's embarrassing that there's a phase transition, but you can fix that in higher order. So that's the bulk. So the important thing I want to say is that for the bulk, you have this temperature-dependent hybridization gap, which also direct, and it's sort of related to the indirect gap. This is sort of contrary to what theory showed yesterday, but nevertheless, this is what comes out of theory. The other thing is that the lowest energy excitation in the bulk is from between the zone boundary and the zone center, so it involves this large momentum transfer, and it's associated with the indirect gap. So the interest nowadays in samarium hexaboride is it a topological insulator or not? I'm going to sort of introduce this a slightly different way from the way that maximum zero would be. And I just say, well, this is a system which has a very large spin-orbit coupling. That's because it involves samarium, large Z. And the other thing is if you actually calculate the spin-orbit interaction in most systems, what you'll find is that the strength of the interaction is inversely proportional to the gap. And we know that the gap is very small. It's only of the order of 20 millielectron volts, as opposed to an ordinary semiconductor which has gaps of the order of 0.8 MeV, like germanium or something like that. The other important thing is if we're talking about surface states, then the form of interaction should have the Strashbar form, which was introduced in 1950. So this is my basic largest interaction, other than the Coulomb interactions in the thing. And this is what I'm going to use to describe the surface electrons. And when you use this Strashbar Hamiltonian, what you find is Dirac, actually a Weyl cone, with an energy dispersion equals tau times c times p. C is the analog of the Fermi velocity, or velocity of light. And tau is the helicity index. This Strashbar interaction has the effect of locking the momentum of the spin, of the electrons to the spin, and gives you this sort of circular pattern in momentum space of the direction. For the upper part of the cone, tau is +1, and for the lower part, tau is -1. The circulation is in the opposite direction. Okay, so this sort of tells you have a Dirac cone, large spin orbit coupling. In the real material, samarium hexaboride, one thinks that there, well, photo emission tells you that there are 3 Fermi surfaces, one at the X point, one at the Y point, and one at the gamma point. There's an odd number of these surface states, so it could be a topological insulator if these states are spin degenerate. I call this a Weyl cone rather than the Dirac cone because I put that into Dirac equation. First of all, comes with a mass. You can take the massless or the ultra-relativistic limit of that, but then you still have the problem of your energies being twofold degenerate corresponding to the spin, so that's the helicity. On the other hand, with the Weyl equation, in the massless limit, you can actually map the Dirac equation onto 2 Weyl equations, one for left moving and one for right moving Weyl particles. Actually, one describes the electrons on one surface of your sample and the other equation on the right. In this case, your Weyl equation, you choose one Weyl equation to represent your surface, you have a unique helicity, and this is really what we're talking about, is topological insulators. Contrary to the normal nomenclature. Okay, so I'm talking about Weyl equation. It's not really that yet. You have to reduce the three-dimensional Weyl equation to two dimensions, which I do by this simple thing, and then you get back to the Rashba Hamiltonian, and you find this this Weyl cone, if you like. And now what we're doing is just putting in Fermi energy, not at the Weyl point where the two cones meet, but somewhere in between, so you have a finite density of states. What I'm showing here is the density of states as a function of energy. It has a simple V shape, and the Fermi energy is going to be set somewhere there. So this is a simple picture of that. Let me convince you that this is describes topological insulators. If you apply a Zeeman interaction, then this nice dispersion relationship becomes that horrible thing there. There's, it's sort of like a shifted, it's like as if you've shifted momentum space by applying the field in the plane, and if you apply a field in the z direction, you actually get a gap in the spectrum. So that in that case, let me just flip over. So the shift in applying a field in the plane actually provides this shift of the momentum at which the cone is centered to some point here. So this is again just looking at the Fermi surface. It's now shifted away from what used to be the origin. And you can see now that in this case you have a net number of electrons with momentum k and no electrons with minus k, so you have a net current flowing, and this is in the ground state in the presence of the field, and so you have a net surface current which can then flow around the system without any dissipation. So this is the ground state. The effect of a normal field, well, that breaks time reversal invariance, and what you find is that there's a mass term which gaps the Weyl cone. So in the presence of the field, the number of states of any energy is not constant. This Weyl cone is cut into two separate pieces where there's a piece where there's no states. So that's a simple description of the surface state. I could have approached this from the normal way, which is to say topological properties are really bulk properties, but I'm just inverting the theoretical argument to start from the surface. Well, what I want to do is to show that there's a possibility of having bulk properties talk to the surface properties in this system. So I want to look at the effects of the electronic excitations of the bulk. So this is a semiconductor. One wouldn't expect much to happen except to energies of the order of the gap. But these materials, I think, like most heavy fermion or F-electron systems, are close to some sort of quantum critical point or magnetic instability. So if we do have F-electrons in our band structure, there's always an RKKY-like interaction between them, which was first evaluated by Doniak using the slate boson method, not for the semiconductors, but for a metal. And the RKKY interaction is proportional to the fourth power of the hybridization. Well, actually, you can easily understand that because the RKKY interaction is proportional to an exchange between the conduction electrons and the F moments, which I call JK, and from the Schrieffer-Wolff transformation, that's proportional to V squared. And so the RKKY interaction is proportional to this Kondo interaction squared times some susceptibility. And that gives you an interaction, and it's the same interaction that you find in the semiconducting or insulating state. So what I'm going to do with this is just simply take the quasi-particle susceptibility from the renormalized bands in the bulk, which I showed in the first transparency, these are the hybridized bands, and calculate the F susceptibility, and it follows the usual RPA type form. And just look at this for a second. The imaginary part of the total susceptibility tells you the density of magnetic excitations in the system. Chi naught is the quasi-particle density. Imaginary part of chi naught is the quasi-particle density of states. Since we have no bands, then within the hybridization gap, the imaginary part of the susceptibility is 0. So that would sort of indicate that you're not going to have magnetic scattering inside the gap. And this is essentially what Andrea showed with cerium 3 bismuth 4 platinum 3 in the 1990s when she was still in kindergarten. However, there's a possibility that there could be an excitation in the system for the RPA if you can satisfy the condition that the denominator is 0. We've just said the imaginary part is 0. Imaginary part of phi 0 is 0. What happens if 1 equals j times real part of chi is satisfied for some frequency inside the gap? And you can sort of say, well, that might be true if the system is very close to a quantum critical point, very close to satisfying the Stoner criterion, which was essentially the same equation, but just at 0 frequency. So that would be a Grandstein property. Well, in that case, just a simple analysis will show that the imaginary part of the self-energy is proportional to a delta function at frequency omega equals omega q. And this is the magnetic exciton. Oops. And this was, the magnetic exciton was first observed in the 1990s, not in cerium 3 bismuth 4, but in samarium hexaboride by Alexeyev. They were also seen in ytterbium boron 12 by Japanese and French groups. Recently, Colin Broholm has seen the same thing in samarium hexaboride once again, but what he was able to do is to look at these excitations at other points in the Brillouin zone, and you can see that these are coherent excitations obeying Bloch's theorem, etc. Okay. Running out of time. So, do they exist? Well, if you take the hybridized band picture, we have this indirect gap involving momentum transfers from the zone centers to the zone boundary. And so I've just plotted out the real part of the susceptibility and the imaginary part, which is 0 inside the gap. Close to the edges of the gap, the real part of the susceptibility shows peaks. And if you put a value of 1 over j, you can then see that you have these magnetic excitons, possibility of magnetic excitons sitting in the gap. Over here I've shown the dispersion relations that you can get out by changing values of j. And you can see one thing, as the thing softens, the amplitude increases. So there are 2 different values of j. And as I said, these were measured by experimentally. So now what I want to do is to say these things can be coupled to the surface excitations. Why should that be the case? Well, if you look at the, I guess, penetration depth, or the depth at which these surface states penetrate into the bulk, then I think Alexandrov has shown that this penetration depth is proportional to c, the Fermi velocity divided by the gap, and you find that these actually should penetrate of the order of 15 angstroms into the bulk. Photo emission experiments will say 60 angstroms or more. But nevertheless, this is a theory I can look at I can be sloppy. Okay, so now what I want to do is just calculate the self-energy of the surface states due to the emission and absorption of bosons, and I think my words are slipping down. As was mentioned yesterday by Jim Friedrichs and Alexander, that there's from phase-space arguments, what you can say is that the imaginary part of the self-energy gets split into two parts. The part below the Fermi surface gets pushed down, and the part that's above the Fermi surface gets pushed up by the typical boson frequency here, which is spin exciton energy. And what that means is for the density of states below the Fermi surface, you have part of this V-shaped density of states. And what that also gives rise to some sort of almost logarithmic singularity in the real part of the self-energy, as shown here, which is extremely temperature dependent, because it involves intermediate states which are at the Fermi energy. And if you look at the density of states, then what you get is a resonance of the density of states at the spin exciton energy, which is extremely temperature dependent. You can plot the dispersion relation out for this system, and that of the quasi-particle band, just looking at where the real part of the self-energy goes to zero. What you would have expected is just these two Weyl cones and to be joined up, but because we have a spin exciton in there, these bands are sort of folded. It's sort of like a mass renormalization of the Fermi surface. This lower band is very, very much broadened because the imaginary part of the self-energy is finite there, and the upper one is not. It's only broadened by presence of Bose-Einstein factors in the self-energy, which should give us sort of a thermal activation part to the self-energy. So does this structure exist? Well, you could actually look at existing R-pairs, K-resolved R-pairs. This is supposed to be at K equals Kf, and what you see is that there is some feature about 5 millielectron volts from below the Fermi surface, which is extremely temperature dependent. And Alex has confirmed this, the existence of this with angle integrated photo emission spectrum, where he took data at 21 Kelvin and saw, 20 Kelvin, and saw this blue curve, and then at 1.2 Kelvin, and just subtracted the difference. What you see is a feature, prominent feature at around 19 millielectron volts, which is the energy associated. You have this feature at 5 millielectron volt, 9 millielectron volts, which is, we think is the spin exciton, and this is just the bottom of the Weyl cone at low temperatures. So I think with that I'll finish, and thank you for your attention.
We have one or two questions. Does anyone have any questions? Yes.
So you are claiming that there is really a coupling between surface and bulk through this
Right.
mechanism.
Right. Right, that's right. I mean, it's based on the assumption that the surface states have this decay length into the bulk, which is quite large. And in that case, yeah, there should be some sort of coupling.
Right. Let's take